Okay, great. So I just wanted to talk a bit about combining JWST and 21 centimeter data for reionization in cosmic dawn science. This is something that we have heard a bit before from Tirth and from Andrei. So I want to present a different take on what they have said and present a sort of very different approach to this problem. I'm going to present multiple results, and all of this work is done by my students, the two Shikhars, Shikhar Mittal and Shikhar Asthana, and Sindhu Satyabolu, all of whom have now become former students and have moved on to different institutions. So we've heard really interesting mentions of JWST in this morning's talks and also talks in the previous days of this conference. But it's worth reminding ourselves that reionization in cosmic dawn is sort of a shared goal between these two great programs, the 21 centimeter cosmology, mainly dominated by SKA at some point, and then the JWST optical, infrared, and UV astronomy at high redshifts. JWST is running various surveys like Sears and Jades that have become sort of familiar names by now. And then eventually, as Isaac Wald emphasized in the morning talk, we will have the Roman Space Telescope, which will add more information to the mix. And the JWST side of things aims to detect UV emitters, so basically galaxies, but maybe also AGN. They don't really detect IGM directly. And then on the other hand, we have our 21 centimeter projects where we have power spectrum experiments dominated by ARTFARC, HERA, etc., eventually culminating in the SKA. And then we have global signal experiments as well, EDGES, SARAS, REACH, all of us know about these efforts here. And then here the aim is very different. Here the aim is to measure the IGM signal, which is expected to be these tiny sort of distortions on the low frequency spectrum of the sky. But again, both are detecting quantities that are very closely related. It's the galaxies and AGN detected by the JWST that influence the 21 centimeter signal. You'll still find that there is very little discussion of this connection between these two probes in the literature. And the reason behind that is combining information from these two sources is really, really hard. And so that's where I want to take this talk. Now, what I want to do in this talk is first emphasize what we are learning from JWST at the moment about reionization, how the new JWST discoveries sit with our understanding of reionization, and then I want to bring the discussion to 21 centimeter and develop some new techniques on doing that. So I would argue that there are three really amazing discoveries that JWST has come up with that are relevant to the people in this room. The first of this is this discoveries of Lyman alpha emitters all the way up to redshift 13. We heard about this in the first talk today. This is remarkable. We wouldn't have expected Lyman alpha emitters to exist beyond redshift 6 or 7 maybe, but 13 is just very high. Then we have a discovery of a new population of AGN at redshift 4 and above. This is factor of 10 to even 100 more in number density than our traditional AGN. Again, this might affect our understanding of sources of reionization. And finally, we have galaxy UV luminosity functions. These were emphasized by Andrei and Tirth, now measured all the way up to redshift 25, actually. And then we know what that means for our reionization model. But again, it's a wealth of data coming, and we are desperate to understand what this tells us about reionization, but answering that question turns out to be quite hard. So let me start by the first attempt we have made towards extracting some reionization information. This is using the radiative transfer models that we have been developing in my group. So this is an alternative scheme than the semi-numerical approach that we have heard a lot in the first few days. Here is an example of one such model. And here what we do is, instead of the kind of things that 21 centimeter fast does, for instance, we actually model reionization using GPU-based radiative transfer using an algorithm called M1 closure. What is the advantage? The advantage is that we achieve very large dynamic range. This is something that Ilian emphasized in his talk. And then, in fact, the speed is amazing. We are faster than semi-numerical models now at comparable resolutions. And then the other thing is that these models are all calibrated to the Lyman alpha forest data. So they are guaranteed to produce the familiar post-reionization universe. The problem, however, the deficiency is that unlike semi-numerical models, these approaches don't come with a convenient parameter handles, the convenient parameter space. So traversing parameter space is hard because we don't know which direction to move in. So that's something that we are trying to do at the moment. So the approach is pretty crude because, again, we don't have these very simple parameters that we could tweak, and we are constrained by the Lyman alpha forest. So one approach is to modify the high redshift end of the reionization history and construct models like that. So for example, here the fiducial model has a midpoint of redshift 6.5, the early model stretches that to 7.5, and an extremely early model moves that to 9.5. And notice that all of these models look very similar at redshift 6. They are calibrated to the Lyman alpha forest. It's only the high redshift end, the high redshift tail that is wagging. Similarly, the other dimension that we could play with is the source model. So if in the fiducial model, we have sources residing in halos down to 10 to the 9, and the luminosity contribution of these sources is proportional to halo mass, we could construct a democratic model where the halo mass remains the same, but the contribution is now independent of the halo mass. So all halos contribute equally to reionization, or an oligarchic model where the contribution from low mass galaxies is suppressed. And then again, you can see interesting effects on the reionization morphology. There is a lot to discuss potentially, but the point I want to make here is that all of these models can be calibrated to the Lyman alpha forest. You can see on the left panel here that all of these models can reproduce the observed mean transmission of the Lyman alpha forest. But then when you look at the predicted reionization histories, you see an interesting diversity on the right panel. In fact, depending on what your precision requirements are in solving reionization, there are very interesting differences at low redshift end in the right-hand side plot that we can discuss potentially. Now, what we can do is we can take this suite of simulations and then confront them with these JWST discoveries. That is one approach to JWST data. So here's discovery number one, the Lyman alpha emitters at high redshift. So now, to see a galaxy as a Lyman alpha emitter, as Isaac Wald nicely explained in his talk, you need the galaxy to be surrounded by a large enough ionized region. Otherwise, you don't see the Lyman alpha. So do these configurations exist in these simulations? So on the left panel here, we are measuring VFrac, which is the fractional volume of the simulation box occupied by regions of size at least R-min. Now, there are three colors denoting our three models, and inside each color are three lines denoting different R-mins. And what you can see is that as reionization progresses, VFrac increases as one would expect. But then on the right-hand side panel, if you now count the fraction of halos which sit inside these ionized bubbles, you see that in the fiducial model, there just aren't any high mass halos in large ionized bubbles. Whereas it seems that you do need this very early tail that stretches out to high redshift if you are to explain the incidence of those Lyman alpha emitters. Now that's interesting because that has a little tension with the CMB measurements of tau. So this plot now shows the cumulative Thomson scattering optical depth as a function of redshift in these models. And you can see the blue curve is the fiducial model, which sits perfectly on top of the Planck measurement. And the extremely early model is discrepant with it at about 2 sigma level. What's interesting, of course, is that the CMB community itself is now debating whether the Planck measurement of tau is correct. And they have published multiple measurements recently, which kind of also seem to be moving in the right direction, but who knows where this will go. We can talk about JWST AGN in the same fashion. Sources of reionization has been a difficult problem. We haven't had much discussion about that in this meeting. Galaxies are notoriously bad at producing hydrogen ionizing photons. So reionization by AGN is really attractive prospect, and many others, including us, have argued that that's difficult because there simply aren't many AGN at redshift 6. But now JWST has discovered hundreds of AGN, and Madao recently in 2024 argued that now the possibility of an AGN-driven reionization model is realistic. So we have built these quasar-only and quasar-assisted models to study this. In a quasar-only radiative transfer model, there's no galaxy contribution to reionization, and in a quasar-assisted model, it's 20% contribution from AGN. We have made some innovations in how AGN are modeled. Our AGNs are stochastic and variable, so we have brought in some wisdom learned from proximity zones. So here are 2 slices from the simulation box. Each point here is a source of radiation. Blue are the galaxies and red are the AGN. Size is the luminosity. And you can see these panels are separated by 10 mega years, and you can see that the galaxies are same in the 2 panels, but the AGN fluctuate. There is a lot to discuss here, but I will just point out that because of its very high recombination rate, AGN-assisted models don't have any problem with helium reionization, as one would have naively thought. So I used to also think that helium reionization would be a problem, but turns out it is possible to construct models with up to 20-30% contribution of AGN and get by with helium reionization constraints. Discovery number three is the UV luminosity function measurements, and we want to now ask how they sit with our understanding of reionization. But here, what's interesting is we also have, in addition to the UV luminosity function, now measurements of this quantity called Xi ion. And the measurements are amazing. They go from redshift 3 to redshift 9. This is Charlotte Simmons' work. Xi ion is the number of ionizing photons produced by a galaxy internally per unit UV photon. And so that's an important measure of the intrinsic production of ionizing radiation. Now, what's interesting is that if you specify these two quantities, our simulation can then come up with the expected value of the escape fraction and the clumping factor. I don't have time to go into the details, but what's remarkable, the reason I wanted to mention was in our previous conference in Stockholm, there was a lot of discussion about these measurements leading to a photon overproduction crisis. And if you now compare our escape fractions and clumping factors with other inferences, it does seem that the picture fits and there is no photon overproduction crisis. We do get reasonable escape fractions and clumping factors, we do manage to agree with the Xi ions and the UV luminosity functions. Coming now to the 21 centimeter side of things, which is sort of the topic of this conference, I now want to ask what is the optimum way of combining information from JWST and 21 centimeter. Again, we have heard about this from Andre and Tirth, and there is work also done from Anastasia Fialkov's group. Jiten Dhanda recently wrote a paper on this just a few days ago. And the traditional approach here is what we do is we build a parametric model of the galaxy UV luminosity function, etc., at high redshifts. And this parametric model is an extrapolation of what we know at low redshift. And very plausible, sort of built up on top of very plausibility arguments. Like, for example, in this plot is one of these parameters, the star formation efficiency as a function of halo mass. And you kind of hand-wavily argue, well, at high mass end, it should be small, and low mass end, it should behave like that, and so on. This is great. This is very useful. But the problem is, there is no guarantee that your parameterization is the sensible one. We just don't know much about the high redshift universe. So one risk is your model might not fit the data. And the second risk is even if it fits the data, it might not be the correct model. It might not have exhausted all the information. So this is what I want to emphasize here. Another way to put this is that the data might require flexibility in the modeling. So here is an example of that from the edges story. So on the right-hand side here is the famous edges measurement in the gray curve, gray shaded region. And the green curve here is one of the best fit models of the kind that all of us have seen and built. Here the depth has been obtained by means of an excess radio background, etc. And everyone is familiar with this Gaussian-like shape. But notice that the edges measurement was famously not Gaussian. It was this box-like Gaussian, flat-bottomed Gaussian is what they called in their paper. Now, what is interesting is that although in every edges-related talk, there are whispers in the audience about that shape, there is hardly any papers discussing that shape and what the reasons behind it is. And the reason is not that people are not interested in, but just that the low redshift parameterization doesn't allow an analysis of that. So in fact, if you think about it, the edges profile requires a very sharp drop, which means the establishment of a cosmic UV background within 25 million years at redshift of about 20, and a cosmic X-ray background very sharply in 50 mega years at about redshift 15, and then there has to be some balancing in the middle. None of this is captured by our parameterization. We continue to do that. If you calculate the chi-square or the p-value, it will be appallingly bad on that right panel, right? So we can now discuss a different way of doing things. And I'm going to present this way of actually creating models of 21 centimeter signal by means of the edges example. Now here, just let me clarify that the use of edges data is just as an example, just because we did it in our paper. You could repeat the story for any measurement, including Saras or reach, or even just drawing an arbitrary signal and applying this to that. So what's the idea? Well, you start by noticing that the spin temperature is a linear combination of the radiation temperature and the gas temperature, where the weight is given by the Lyman alpha coupling. And then the spin temperature gives our observable delta TB using this famous equation. Now, what's interesting is that everything that JWST sees fits in that X alpha or the TK. right? X alpha is the UV properties of galaxies and TK is the X-ray properties of galaxies. And then on the left-hand side is our 21 centimeter. So essentially, we need an intelligent way of inferring JWST parameters from X alpha and TK when all we can measure is delta TB. Here is one way you could do that. So we can start by formally inverting that equation. And we can say instead of writing delta TB as a function of TS, we write TS as a function of delta TB. It's just 1 minus that thing and multiplied by TR inverse. And then we can invert the equation relating the X alpha and TS to write the second equation here. Once we have that, then X alpha can be used, this X alpha prime can be used to obtain a candidate solution for the J alpha, the UV flux from the galaxies, where we can just supply it with a candidate solution and it will multiply this with this factor and give us the true solution. J alpha is not what JWST sees, so we want to connect J alpha, the flux, to the volumetric emissivity, the UV emissivity of the galaxies, the epsilon alpha, which is what JWST sees, which is what is the integral under the luminosity functions. Now that's complicated because photon redshifting has a more complex behavior, but that's no problem. What you can do is you can just plug in a factor M alpha here, which is a function of redshift, which is a function, not a number, and then you can just solve for it iteratively. You can start with M alpha equals 1, which is just a standard parametric model or something, and then it will tell you what is the M alpha that's required, and then the M that's resulting out of that iterative procedure gives you a measurement of the epsilon alpha. Now this process actually just in 3-4 iterations converges and gets you the solution. And this is not, the idea is not new. This is called relaxation method, and it was actually invented by someone called Richard Southwell in the 1930s and 40s, who has a whole textbook called Relaxation Methods in Theoretical Physics. So if you have any complex data set from which you want to retrieve parameter values, before you fire your MCMC at it, you could just do relaxation methods, and it works really well, regardless of linearity. So here is the solution now for what I just did there. Here, what is shown on the left-hand side are the 3 temperatures, and the right-hand side is the comparison with the data. Notice how good the model is. The blue curve is now this model, and it fits it perfectly. It has got that rapid evolution on the both sides. It has got that flat bottom. You can see that the temperature, spin temperature evolution on the left is very non-trivial. There is no way a simple parameterization would have predicted that this has to be the case. The chi-square would be insanely good on the right-hand side. In fact, we could now go ahead and infer this using the discussion we had about population 3 stars, for instance, where using this kind of plots where the right-hand side shows the UV flux and the X-ray flux obtained from that analysis, and on the left are these modification factors, the M factors. And then clearly what Edges says is that at high redshift, you had better had no Lyman alpha flux, because then the absorption trough would have started at high redshift. And then you need this burst in Lyman alpha for a rapid drop in the spin temperature and so on. So we can now ask, well, is this possible in realistic scenarios? And here we found that POP2 IMF cannot produce this sort of Lyman alpha densities. So you are learning real properties of those stars from this analysis. Again, I want to emphasize this information would have been lost in a conventional analysis. We can now generalize this and study degeneracies. For example, we can say, no, I want to restrict the Lyman alpha emissivity to a certain range because I don't have any stars to produce what the data needs. And then the retrieval tries to balance it out by modifying X-ray emissivity. For example, here it says, okay, if you can't give me tight coupling between the spin temperature and the kinetic temperature, let me raise the kinetic temperature so that I can get the spin temperature up. So it boosts the X-ray emissivity by a factor of 8. Again, if you look at the models, this is very hard. But again, you can get great fits. So here is another model where now the X-ray has been modified. You can see the kinetic temperature doing very strange things now. And again, this would be difficult to obtain in a traditional analysis. Or we could actually, instead of obtaining X-rays and Lyman alpha emissivities, ask it what are the star formation rate densities that we need for the data. And so here is the result. Again, that's that M factor, and here is the star formation rate density as a function of Z. What you see in the dotted smooth line is the conventional model extrapolated to high redshifts, and then the solid blue line is this predicted model. And you can see what's going on here. At high redshift, it wants a rapid decrease in the star formation rate because then you would move the signal to high redshifts. And then it wants a little burst because it wants to get this Lyman alpha coupling start rapidly, and then again an increase at low redshift. we could continue in this way, but this is where the beauty of the method is, in my opinion. What you can now do is you can assign UV luminosities per unit star formation rate, as we all do in JWST data analysis, and start getting JWST observable using this method. So if we do that and put some limiting magnitude for a JWST survey, on the left-hand side, we have a predicted number density of galaxies that James Webb will see as a function of redshift. Again, it has that shape we saw on the previous slide, and the smooth curve is a more simpler model. And then we could also talk about excess number of galaxies that each of these famous surveys will see relative to a more straightforward extrapolation. So what I want to sort of suggest is that this might be an interesting direction to look at for a more model agnostic connection, because I think high redshift universe is something we know very little about. And so this, I think, complements our traditional approaches really well. I think I want to end there. What I wanted to convey was that JWST is producing a wealth of data for reionization and cosmic dawn, and those of us interested in 21 centimeters should pay some attention to that. Current reionization simulations appear to be consistent with what JWST is finding, but when you bring in the 21 centimeter detail, things are a bit hard. And what we are suggesting is a new way based on relaxation methods that could be an interesting approach. And I think what I wanted to highlight was that these methods are not only very efficient, but they also potentially uncover information missed by conventional analysis. I'll stop there.
Thank you. We had plenty of time. That didn't include question time, so you.
Oh, it didn't. Sorry.
So I think we have plenty of time for questions. Maybe one comment on the edges shape. I think now they have presented at several meetings. I don't think it's been published yet. The edges 3 results, the preliminary results, where it shows a much more smooth feature, less square-looking feature, but the depth is still the same. But I don't think it's been published yet. So, questions? Yes, there.
The AGNs, do they ionize isotropically, or if it is not isotropic, then what effect will it have? It's supposed to few megaparsecs, right?
Yeah, so it's not isotropic, but then what you are seeing is also what a typical point will see. So I don't know, it's like a statistically isotropic thing. So you are seeing the type 1 fraction, which is sort of, which you would expect to be the type 1 fraction seen by any point in the IGN.
No, but how the reionization progresses through them will be different, right?
There might be differences in how the ionization front progresses near the sources, but I guess far away from the sources, it shouldn't matter that the source is not isotropic. Even galaxies are not perfectly isotropic.
Yes.
Yeah, Girish, about this recovery of star formation rate from the 21 centimeter signal, I understand that the 21 centimeter signal will give you the whatever X-ray emissivity and the Lyman alpha flux, but there is a degeneracy from that to the star formation rate, right? I can decrease the star formation rate and make them X-ray efficient and Lyman alpha efficient. So this excess of galaxies is not a robust or model independent result.
No, it's a degenerate prediction with X-ray, and as I showed you, we could infer the Lyman alpha putting a prior on the X-rays. We could infer X-rays putting a prior on Lyman alpha, and you could put a prior on those parameters and get the star formation rate. The robustness doesn't come from the fact that there is no degeneracy. There are degeneracies. There will be degeneracies. The robustness comes because there is no parameterization. So what has been done in the star formation rate retrieval is that we have fixed the values of the X-ray efficiency per unit star formation and the UV efficiency per unit star formation. And then all that was left for the retrieval procedure was to...
There's the parameterization, except that you have fixed the parameters.
So we have fixed X-ray per unit star formation rate and UV per unit star formation rate. Sure, yeah. What I meant, there is no, when I said there is no parameterization, I meant not on redshift. Yeah, sure. Yeah. In fact, even puristically, there is a parameterization even on redshift. It's just that this is like a very large number of parameters. Sure. Yeah. The point is not that. The point is there are more than 2 numbers, and you are retrieving those numbers via inversion rather than MCMC.
So I guess following up a little bit on this, I mean, this whole model independent thing is an age-old question. Like they use it in the CMB when they want to model the EOR history, for example, as just a function of redshift. But I think it's a bit of smoke and mirrors in many ways, because even if you go directly in this and model the delta t as a function of each frequency, you're just throwing all of your model dependencies into the priors in some highly complex, covariant shape. And I have no idea how to write that covariance matrix, whereas I sort of know how to write galaxy formation. So I would argue actually against a abstract thing, because in my prior volume, those evolutions that you showed with like wiggles that shoot up, I would give those very, very, very low prior probabilities given what we know about structure formation. And I think following up on that, this whole approach of using this weird thing as it's kind of a pseudo likelihood to infer. We showed this in this paper by Kang last year, that really this flattened Gaussian approach gives you completely the opposite result as compared to just actually putting the likelihood in data space. What people do is they take the best fit flattened Gaussian and then they just put some kind of chi-squared on depth and width and all this. But if you actually go to data space, you can see that you don't recover that shape at all as soon as you start including more foreground terms and or systematics terms. So it actually gives you completely the opposite result in that paper where we argued edges actually disfavors exotic models if you do the likelihood properly.
Right, so there's a lot there. I didn't mean to threaten semi-numerics or parametrics. I think the two heroes of semi-numerical methodology are barking at me now. But I think one of the things is I would dispute with the assertion that your priors are robust, because we just don't know anything about population 3. We just heard from Eric that we don't know anything about what your M-min is or your R-max is. Secondly, so I think what you are right at is...
I agree. It's a relative statement.
Yeah.
Then I can on like the covariance of delta t at redshift 8 to redshift 9 or something like that. It's more easy to put priors. You might not agree with them. You might not agree with the model, which is perfect.
Which is perfectly fine.
This is why in this paper, for example, we did 21 models.
Exactly.
And then we compared evidence. I think that's the way to go. Like,
so I think there's nothing wrong in what you are doing by using parametric priors. Absolutely not. But there's also nothing wrong in exploring other options, because
you have to confront it with a physical model.
But then you have to confront it with the physical. I never want to claim that this is
a perfect topic for a beer tonight. I think we do need to move on. Because we can go on and on this.
This is
thank you again, Girish, for a wonderful talk.
Thanks.
So